we're talking about sound here, and sound is measured in bells. Now, a bell is actually a very loud, very loud sound. So what we do is actually we're going to be using decibels. Yep. And what is a decibel? A decibel is just this. We got a bell, we divide it by 10, and that is a decibel, 0.1 bells. And that's equal to 1 decibel. Okay? Now, that's how we write it. A small d and a big capital B. I'm going to give you an idea of what decibels are. In a normal office, for example, you walk into an office, and then you're going to find, if you got a sound meter, that room is going to have a sound level of 50 decibels. And that is a good, comfortable sound level for a productive office where people working there is going to be working healthy and going to be productive, because this is a good sound level. Now, if this room had, for example, 80 decibels, that wouldn't be that healthy. Now, why you might have this level of sound? Maybe because you're near a road and you have very thin glass panes, and the sound from the street is getting into the office and is building up together with the actual noise happening inside the office. This is not a healthy place to work. Now, this sound needs to be diminished. And a building engineer will put some measures into place. It could be, for example, making a glass pane to be thicker. Now, for thermal resistance, the glass panes, for example, if it's a double glass pane, we want them to be closer, but maybe 20 millimeters apart. It will be a good width of separation. What we don't want is the air here, the gas there, to start moving and creating convection currents here. So that's why we want to keep that distance small when we're looking at thermal efficiency. But when we want to look at soundproofing, maybe we want to make this wider. This will increase, having two glass panes is going to increase thermal efficiency as well. It will not be as effective as if the panes are closer, not too close either. There's a balance there, yeah? But if we are looking at sound efficiency, we might want to separate the panes and make them wider. Now, we can find a compromise where we got some thermal efficiency and also we got some sound proofing. And let's remember we can have 3 panes. So if that's needed, that can be done. It costs money, but we're going to be working in an office with these levels of sound that is unhealthy. So that is where we are. Now, if I was not using decibels for my calculations, I should be using bells. And then I will be writing 0.5 bells, which is not so interesting in terms of using decimals when we're measuring everyday sounds. So for us, it's much better to use as the basic standard unit the decibel for measuring how loud a sound is. Now, I'm going to say something that you all know, and is that sound travels at different speeds in different materials. air, we're going to say that sound is going to be traveling at this speed. Now, imagine a metal rod. We hit it with a hammer. The sound is going to travel much faster inside a metal rod. So different materials, different speeds for sound. But this one is in air. We're going to take air as having this velocity. Now, this is important for the calculations we're going to be doing for our assignment. So I explained a little bit how sound is measured in bells, actually in decibels. I explained what a bell and what decibel is, and I'm giving you some parameters and talk about double pane glaze and etc. But now we are looking at the speed of the air, of sound in air. Now, if there is not air in a room, there's no gas, there's nothing there, it's vacuum, sound is not going to travel. Why? Because sound is just a distortion in the air. It's a wave. So what happens is when, for example, I'm talking now, I produce a distortion in the air, like a wave, and this reaches my ear. And at the end of my ear, there is like a membrane. I'm going to put my hand like a membrane. And it's like a drum. And when the air hits that membrane, it vibrates like that. That's what's happening. That's what's happening in the side of your ear. You got this drum, and it's moving like that constantly. And now, attached to this membrane, there is like 3 little bones. And as I move, these bones move, and they give to the brain an electric signal, some electric impulses. And the brain, from those impulses, is going to work out what that sound is. Yeah, it could be an explosion, it could be a guitar, it could be me talking. In fact, that's what's happening. In the moment you are listening to me, that is what's happening. And these waves have a frequency, and these waves have a length. And we're going to do just a very simple calculation. Now, I got some light coming into my room, and I got some shades you can see here, but let's ignore that. I'm going to go with this formula, and this formula is V equals F times lambda. Now, lambda is a Greek letter, and what everything in this formula stands for is V is for the velocity, this is the frequency of the sound waves, and this is the length of the waves, so it's wavelength. Okay, very good. Now, later on, I'm going to be explaining another exercise where we are looking at this frequency for certain calculations. Now, the wavelength is measured in meters. Velocity is meters per second. But frequency is measured in hertz. And the abbreviation for a hertz is Hz. Okay? Now, what I'm going to calculate now for you is, for example, the wavelength of a sound which has a frequency of 50 hertz. Okay? Now, I'm going to rearrange this formula, and the first thing I'm going to do is to invert the equation. So I'm going to write that the frequency times lambda, well, with the lambda I draw, equals the velocity. Now, I want to make lambda the subject of the equation. Lambda is a Greek letter, lambda. So lambda is going to be the subject of the equation, and I have decided I'm going to divide both sides of the equation by the same number. In this case, is f, frequency. And that's what we got. We got lambda being equal to velocity and frequency. Very good. Now, let's imagine. No, it's not an imagination. We know that the frequency is 50 Hertz. I'm going to write 50 here. And then I'm going to write the speed of light, the velocity, and I'm going to take it at 330. Why? Because I want, and I can. And what I got is that if I divide this figure by this figure, I'm going to have 6.6. And what? What are these 6.6? But if it is a length, is meters. And I'm just giving you a little game of formulations here and calculations. I talked a little bit about stuff, and I see you in the next video. Goodbye.